In this video, we're going to learn about acids and bases, some of their basic characteristics, and how they interact with one another. So first of all, let's look at some properties of acids. Some of these will be reviewed from grade 10 science when we studied acids and bases briefly. So first of all, acids are sour and they're corrosive, which is why you shouldn't taste all acids, because the corrosivity might actually be dangerous to you, but all acids would have a sour taste if you could taste them. Acids also react with metals to make hydrogen gas and metal salt. The metal salts will usually be soluble. They will react with carbonates to make carbon dioxide as an addition to the salt and the other materials. They turn blue litmus paper red, and acidic solutions can conduct electricity, which is why your electrolytes and batteries are usually an acid or an acid paste. Bases, on the other hand, are bitter. They can also be corrosive. They're slippery to the touch. So if you think about soap, if you've ever tasted soap, it's bitter tasting and it's also slippery. Soaps are bases. Bases don't react with metals or carbonates, so there would be no reaction if you interacted them together. They turn red litmus paper blue, and basic solutions also conduct electricity. Now here's something that's interesting. You'll sometimes hear people refer to bases and alkali. So there's two different types. So all alkali are bases, but not all bases are alkali. So bases all neutralize acids, but alkalis are bases that are soluble in water. So sodium hydroxide and potassium hydroxide are soluble in water. Not all of these are as soluble in water. So alkali are soluble bases. All bases neutralize acids. So we're going to briefly talk about the Arrhenius theory. It was one theory of acids, but we don't cling to this one. We're going to focus on the Bronsted-Lowry theory of acids. In your grade 12 chemistry, you'll also talk about Lewis acids, another theory for the acids. So an acid in the Arrhenius theory is a compound that dissociates in water to release one or more hydrogen ions, also known as protons. Remember, when you release a hydrogen without its electron, all that's left is a proton. So the example would be hydrogen chloride or hydrochloric acid dissociating into a proton and then the chloride ion. The chloride would keep the electron from hydrogen to make this a proton and then the chloride ion. And then a base is a compound that dissociates in water to release one or more hydroxide ions. So sodium hydroxide does break apart into a sodium ion and a hydroxide ion. This is a bit faulty because not all bases will do this. So some problems with the theory. When an acid dissociates in water, it releases a proton or a hydrogen ion. This proton then continues to react with water to form a hydronium ion, so H3O+. So sometimes you will see this, and it means the same thing as the concentration of hydrogen ions. So this is interchangeable with H+. So these two things are interchangeable. So the hydrogen ion will form hydronium with water, but in the same molar ratio. So you could see this or this in calculations, and they mean the same thing. Some chemicals react with water to release hydroxide, but they don't have hydroxide ions themselves. So for instance, ammonia is a base. It reacts with water when you dissolve it in water to make an ammonium ion and a hydroxide. So indirectly, hydroxide is being released, but it's not being released from the base. It's being released from the interaction of the base with water. So the Bronsted-Lowry theory of acids and bases is the one that we're going to be talking about. So an acid can be defined as a substance that gives up a proton, so H+, and a base is a substance that can remove a proton from an acid. So any negative ion can be a base in Bronsted-Lowry's theory. So if we look at this example, we have hydrochloric acid reacting with water, and in this case water is acting as the base. This donates the hydrogen ion, So this becomes H3O plus with the hydronium ion and a chloride ion. So this one is donating its electron. This one's taking its electron. So this is the proton donor, so this is the acid. This is the proton acceptor, because it accepted the proton, and it's the base. An acid-base reaction involves the transfer of a proton in the Bronsted-Lowry theory. So any substance can behave as an acid, but only if something else is acting like a base, and vice versa. So for instance, a conjugate acid-base pair are when you have two ions or molecules linked together in a reaction by the transfer of a proton. So a base receives the proton to become its conjugate acid, and an acid loses a proton to become its conjugate base. So we're going to practice with this. So here's an example. We have that same example we had before. Hydrochloric acid breaks apart into chloride. So remember, it's the acid. So this is the conjugate acid, or the acid, and this is its conjugate base. And then this is the base, and it becomes its conjugate acid. So there's always this give and take. So when this one gives up its proton to the base, it becomes a conjugate base. So it's the acid becoming the conjugate base. This is the base becoming the conjugate acid. So these are each conjugate acid-base pairs. So you need to be able to recognize those pairings. So let's look at a second example. So in this case we have ammonia acting as a base. So it's going to take an electron and a proton from water, which is going to act as the acid this time. So it's donating. So water donates to become hydroxide. So this is the acid and this is the conjugate base. This is the base. It's taking the proton from water and becoming ammonium. So this one is the base and the conjugate acid, and this is the acid and the conjugate base. So remember, the one that gains a proton or gains a hydrogen is the base and the conjugate acid, and the one that gives its proton away is the acid and its subsequent conjugate base. So the acid and the conjugate base differ in just one hydrogen ion or a proton. So, water. Is it acidic or is it basic? Well, water's known as amphiprotic. It can act as an acid or a base depending on the situation. So in the first example that we looked at, water was acting as the base with hydrochloric acid. In the second example, water was acting as the acid with the ammonia, and it donated its proton to ammonia to become hydroxide. So some other amphiprotic substances are the hydrogen carbonate or bicarbonate ion, the hydrogen sulfate ion, the hydrogen phosphate ion, and then the HPO4 2-. So all of these are examples of amphiprotic. They can go either way. So this one could take a hydrogen, or it can give up its hydrogen. It can do one, either or. Same with this one, same with this one, and same with that one. So they could take or give away. So one thing that you are required to do, and these won't be listed in the data booklet for IB, you need to know the names and formula of common acids. And again, the more you practice with them, the more you'll become familiar with them. So hydrochloric acid is one that we'll use quite a lot, H3Cl. Another one, sulfuric acid, H2SO4. Phosphoric acid, H3PO4. Nitric acid, we won't use as much, but it might come up. Ethanoic acid, it's another word for acetic acid or vinegar. We use that a fair bit in our organic units. Carbonic acid, when we talk about ocean acidification and acid deposition, you'll talk about carbonic acid. You may even talk about it in biology when you learn about blood chemistry. And then benzoic acid will be used in your organic chemistry unit. Acids can also be monoprotic, diprotic, or triprotic, depending on how many protons it can give up. So for example, H2SO4 is diprotic. It can donate 2 hydrogens. So the first dissociation, sulfuric acid will donate 1 hydrogen ion and become this. And then the second one, it'll give up its second to become the sulfate ion. Now, it is also required to know a few of the common bases. They're a little bit easier to remember because some of them are the evolved polyatomic ions that you already had to become familiar with, like calcium oxide. That's, if you see the name, you can come up with the formula. Copper 2 oxide, same thing. Sodium hydroxide, we have to know the hydroxide ion, so that one's helpful. Lithium hydroxide, calcium hydroxide, barium hydroxide, ammonia, and ethanamine, again, will be used in organic chemistry. So these are all ones that you would possibly use throughout your IB chemistry syllabus. So we're going to take a look at some of the reactions of acids. So remember, acids react with metals to form a metal, salt, and hydrogen. So in this example, we have zinc reacting with hydrochloric acid to make zinc chloride and hydrogen gas. Acids will also react with bases, so they form a salt and water in the neutralization reaction. So sodium hydroxide and hydrochloric acid make sodium chloride and water. So when you react an acid with a base, you always end up with a salt plus water. When an acid reacts with carbonates, you'll form a salt, you'll form water, and you'll form carbon dioxide. So this is the reaction that happens between like vinegar and baking soda. You can also react hydrochloric acid with baking soda to make sodium chloride, water, and carbon dioxide. Now, you've probably heard of antacids. In fact, you may have taken an antacid or two in your lifetime. So antacids are medications to treat heartburn. They're usually metal carbonates, hydrogen carbonates, or insoluble metal hydroxides. And these don't tend to be strong acids for a reason. You don't want to, or strong bases for a reason. You don't want to eat a strong base or a reactive base and then possibly cause some damage to your body that way. So what they do is they react with the excess hydrochloric acid in your stomach to relieve the symptoms of the acid reflux. And remember, some of these carbonates, if you react them with carbonates, you'll also form carbon dioxide. So then you'll produce some bubbles of gas, and that might actually cause you to have some burping after taking some of the different kinds of antacids. So we'll take another look at a neutralization reaction. So you'll start with your parent base and then your parent acid. So the hydroxide breaks off and goes with the hydrogen to form water, and then the metal in the base will react with the remainder of the acid. So in this example, sodium hydroxide and nitric acid form sodium nitrate and water as your byproduct. So this would be your salt, and this is your water. And then finally, titrations are techniques used to determine the unknown concentration of an acid or a base. And you would do the following. You would put your base in the burette, your acid in the flask. You'll add an indicator. We often use phenolphthalein. And then you titrate. And you keep adding until you reach your end point, so a color change will happen. With phenolphthalein, you want to make your end point when it turns just slightly pink but not fuchsia. And it just needs to last for about 10 seconds. It can disappear because the phenolphthalein actually will react with the base and make the color disappear for a while. And that's not something to worry about. If you keep adding base, you'll end up with the fuchsia color. So you want that 10-second light pink, and then if it disappears after 10 seconds, that's okay. It just needs to persist for the 10 seconds.